All right, guys. So thank you very much. Kind of different being in a technology session when we're actually a software company and not a hardware company. So, we do need hardware to run. So, we'll go through a little bit of what VAST does. Does anybody here not know VAST? Just by a quick show of hands, has anybody not heard of us before? Ah, brilliant. Cool. So I'll just go on the back end there. Basically, out of stealth in 2019, we launched our first product. We're 5 years old, so when we compare to the industry giants that are out there, we're still fairly young in that sense. But in the sense of our leadership and what we're doing from a technology perspective is trying to push the market to go bigger and better all the time. And that's why our focus on software has been so important. So just really in the sense of what we launched in 2019 was the data store. And this data infinity circle is really about us providing a data management platform for our data centers. Now, irrespective of whether it's HPC, AI, backup, or so forth, our focus has been to provide a highly scalable and performant data store. Moving along in the sense of managing our data was being customers pushing us to say, working with file systems is very difficult. How do we actually get control of the metadata that runs in? Can you expose the metadata of the file systems that run there? So introduced our database in 2020, and database really is a sense of giving you structured access to your unstructured data. Right? And then earlier this year, about in June timeframe, we launched the data engine, and this is the ability to run SQL queries against that database. So think of it in the sense of looking at it in this synopsis is being able to ingest the data into the data store at a protocol of your choice. Right? Being able to then query your data from a SQL perspective, right? And then being able to run that natively on the storage. Now, when you start looking at AI data pipelines, that's kind of coming into a sense of making sure that it runs as close to the data as possible, right? So if I'm bringing in Parquet files, I'm bringing in text files, I'm bringing in CDR records, whatever it might be, it's the ability to use something like Kafka or Python to suck in that data and put it into the database, right? Once it's in the database, I can then run something like Trino or Dremio, Python, Arrow to then run SQL queries against that tabular format, right? And then working with NVIDIA, we're actually looking at putting GPUs into our storage controllers or into the industry storage controllers that we have in some of the x86 servers, and then actually running our query engine and our NIM process. If you look at NVIDIA NIM modules, is being able to then run your modeling and your transactions directly on the storage. So come and have a chat to us if you want to go down that a bit more, but I really want to do focus on the HPC side of it. One of our concepts that we've got from a data management point of view is data space. Now, the concept of data space is the ability to run your software anywhere that you choose, whether it be on-prem, whether it be on cloud, whether it be in a co-location, but it's around the access to data. You can just think of researchers traveling between Joburg and Cape Town and being able to access the data that sits closest to them from a data center point of view. So I could have potentially a cluster running in Cape Town. All my jobs and my big data is sitting down in Cape Town. My researcher goes to Johannesburg. There's a cluster locally that's there. Might not have a copy of the data, but it'll give them access to the data locally in Cape Town. When I start needing to work with the data, I can do a prefetch and bring that data back into Johannesburg, process locally, and then copy it back down. So in that sense, it gives you that the ability to quickly move and access data where you want, when you need it, and how you need it. Think of it again, if someone's running a project in cloud, how quickly can I move my data between cloud and on-prem as well? Yeah. This is the ability of focusing on software and not hardware. Right, so what did we do? If you look back at Google, when Google launched their Google file system, they came out with a white paper in 2003, and most storage vendors, and I used to work for one, focused on building solutions based on the GPFS file system or the Google file system at that stage. Now, no disrespect to the hardware vendors that stood up here before, but I think of hardware at a point, working for Dell for 12 years like I did, when something has a model number, it kind of dictates that there's a limit or a capacity or performance limit of that unit. It's very much like my credit card and my wife, right? My wife sees a limit as a target, right? So very quickly, if you think of it in that sense, researchers, users that we work with in this country push hardware hard. right? If you tell somebody that you can do 2 million IOs in a setting like this, guess what they're going to do? They're going to walk out of here and they're going to write a script or a performance tool that's going to get you that 2 million. Damned if you don't, right? So what we've had to look at in the sense of coming to market was we couldn't rely on these architectures at scale. When you're talking about big data and the number that was up there in the sense of exabytes is real. You know, we're delivering single global namespace clusters today in exabytes, right? We don't talk about petabytes anymore. We don't talk about terabytes. That really terabyte discussion and petabyte discussion is for structured data, right? So what did we do? So we introduced this disaggregated shared everything architecture. Now, why doesn't it work? And you know, talking to researchers, talking to technology experts in this space, the biggest thing around, and you know, dare I say it, like a GPFS, Lustre file system, scale-out software defined, they all have a limit. There's all trade-offs. And the biggest thing I would put down is probably the metadata scaling. Metadata scaling is difficult. You know, the more we add in, and to maybe show it a bit better, you know, the more that we put into the clusters, you know, things need to happen. And there's a bit of trade-off. If I need more performance, I add a unit of measure. And that unit of measure could be another x86 server, right? That x86 server's got CPU, network, memory, and we keep going. But every single piece of that kit that sits there is part of the data delivery, right? Now think of it in that context. Every single server needs to know what every single other server is doing at every single point of the day. The bigger these clusters get, the more they rely on that east-to-west traffic. That east-to-west traffic is literally becoming an internal communication issue and not a data delivery resolution in that sense. So we needed to design differently. The other thing is, like, you know, you could think of licensing in that sense, but I know we like to use open source, you know, and open source does lend itself quite nice to this. But when you have 3-4 days of downtime because storage is an issue, that impacts everyone else in the chain above you, right? So what did we do? Well, we needed to redesign. So one of the things we did is we actually split the architecture out. We split the intelligence away from the logic. And in that sense, what we've did is we introduced the concept of a C node and a D node, C node being our compute layer, and a D node being the disk layer or the data storage layer. And in that sense, in between there, we introduced an NVMe fabric. Initially, we worked with Mellanox, but we have done Cisco, Arista, and so forth in that sense. And it's just in a sense if a customer says to us, hey, we're using, I don't know, HPC, for instance, you know, we'll work on that and try and certify that through. But that also gives customers the choice of InfiniBand or Ethernet. I heard the question just now about, you know, NVIDIA GPU direct storage. You know, when you're talking about HPC and HPC AI, that starts dictating what kind of communication level you're using in the DC as well. So, you know, so what we've done there is you'll see that the C nodes will literally run your protocols, and D nodes is where we're going to store the data. Every single one of these C nodes can see every single SSD that's in that architecture, which means that if every single C node can see every single SSD, we don't need to worry about the partner next to us. And typically, we can actually have a failure of N-1 or N+ in that sense. So I just need one C node to be able to see the data, right? Think of that in the sense of a software-defined platform. And as I showed you on the slide before, one of those nodes go down, performance starts going. Second node goes down. If I've got 3 copies of the data, performance will go down. Potentially, you even lose the cluster. In our sense here, we can lose literally, out of 4-node cluster, we can lose 3 nodes and still run. Okay. Just stop me from a questions point of view, but take it one step further. Because of the way that we've designed this environment, when the vendors bring out new kit, H3C brings out a new server, Huawei brings out a new server, Dell, HP, is the biggest thing we have here is we need to take hold of the new CPU performance that we're getting. Potentially it could be 128 SSD stick in the bottom or 200 new ruler from Intel that we need to adopt. A lot of the times that means that we need to forklift upgrade to get to the new kit, right? From the design that we have in this stage, we can put more CPU in on different generations, and we actually support 4 different generations of CPU today. And that's because we've only been around since 2019. From an SSD perspective on the bottom end, we've got clusters running 7, 15, 30, 60, and now 120. in the sense of mixing and matching SSDs in there. So in that sense, from a scale point of view, I'm giving the customers the option to say, well, look, Dell's the flavor of the month. Let's get the Dell server, and potentially we can evac something out that might not be running efficient, or just keep it running because it's still working well. Okay. Any questions? We keep going. So a couple of innovations that we brought to the market, because we hung our hat on x86 servers, Intel AMD for the compute nodes, the NVMe fabric, and then obviously storage class memory and hyperscale flash, PLC in that sense. Those are the three technology pieces that we've hung our hats on. So we needed to do something to make sure that we could look after flash. QLC is not great. So we introduced something called Foresight. Foresight's just really in the sense of placing data where it needs to be at the right time, at the right price, at the right performance. The next one is locally decodable erasure codes. Every single SSD, if you remember what I said, every single SSD participates in the data transfer and in the data placement, which means that we need to think about how we look after data in the sense of resiliency. So we use locally decodable erasure codes. If you're looking at a rather large system, some vendors will give you 20 to 35% of their overhead that they need to look after that, and that could be parity, it could be whatever, in the sense of cache. We basically, at 150 disks or even at 67 disks, we only look at 2% overhead, right? We basically use a full parity bit code with our locally decodable erasure codes. And then the other thing is similarity, and I think, every single vendor should be doing this hands down. I think, the first two, compression is something, and you'd say like from a high performance computing point of view, is that really relevant? Because sometimes that data is so unique, it's always different. You're not gonna get dedupe, you're probably going to get compression. So, when you talk about vendors, then they'll say, we do fixed block, dedupe, which means that it's a very, either 32K, 64K block that they compare. And if this block's equal to that block, I just have a metadata update and I store once. What we've done is we've actually loosely used a variable block size with similarity. Just think of it in a sense of a window. I can move the window left and right and look at blocks and see if something looks the same. Which means, and I use the word accelerated dedupe, it just means that we can look at compression and get much better compression. The better the compression, the less hardware I need, right? So I'll run through this quickly. So we're still pushing for 6 nines availability. Now, as a software vendor saying, we're trying to push 6 nines availability, that's because our software runs on hardware that we manage, right? The best value from a data reduction point of view, don't need to touch on that. The guy spoke about efficiency. If you're using less, you need less in the data center. I mean, we've seen data centers, and I'll talk about it later, but we've seen data centers running 60 kilowatts, 70 kilowatts in a data center. If we're running 3 to 1, that means, in a 2U space, we're doing 9 petabytes. That's huge. Right, so a little bit more funky build slides. This is typically what a deployment would look like, and this is what we're trying to solve for from an HPC perspective. Generally, what we've seen, and I've seen this in a couple of data centers now that I've been to, is that we build silos based on that technology at a time. It could be because today's flavor of the month is Lustre, next week it's going to be GPFS. Maybe potentially we just need a NAS for user directories. And what happens is we have stranded pieces of storage in the data center and islands of storage that potentially could be used elsewhere. And you generally can't move storage very easily between these clusters because they've been built for purpose. And so, we call them purpose-built storage islands. What VART's strategy in this sense here is to basically be able to allow our data centers to go for one universal platform, no tiering, right? And that means that I can choose the connectivity that I need for my HPC cluster. NFS over RDMA, we talk about parallel file systems. GPFS Lustre, we challenge that with NFS over RDMA. And we actually get better scalability and performance on that. The other one there is GPU Direct. So one of the big things with GPU Direct is, what the guy said from Huawei, what we're trying to focus on there is to offload the storage functionality that tends to happen in the GPU. If we can offload that function to the storage and let the storage handle storage functions, then the GPU gets freed up between 30 and 40% to just focus on what it needs to do and not manage the storage at all. So that really is the focus of the NFS over RDMA component. And then again, why do the users need to be in a different environment? We normally talk about scratch, space, user home directories. It doesn't need to be on a different platform. If I can be multi-protocol at the bottom and support different access control methods, whether it be SMB, POSIX, some form of ACLs, we can consolidate all of that storage. Now, what I'm not really, let's say what we could be addressing here as well is data mobility. If I'm in the same platform, I don't need to copy data. And that's one of the big things that we find with HPC environments is copying data from one environment to another. If I'm all centrally minded, I can snap and mount a snap clone. Or I can just move the data to where it needs to be and give access via the protocol that I need. All right. Guys have spoke a little bit about the Intel and AMD spaces, and yes, we do need them, both for HPC and for AI. But in the sense of where we're focused is bring the CPUs that you need. From our perspective, we will service the clients at any rate. So again, from a protocol point of view, it's going to be a file-based protocol. It's going to be an enterprise NAS system at scale and at performance, right? I don't know if anybody has heard of Cerebras, but if you haven't, it's a very good platform. But Intel, AMD, NVIDIA are still the leaders by far when it comes to the GPU space. Right. In the technology session later, I'll be talking a little bit about tech, but one of the things we tend to look at and we don't focus enough on it is that performance and scale. We talk about 15 times performance benefit over luster, right? And that's from a customer. That's not just us saying, hey, we're fast, right? From a resilience and security point of view, zero downtime is our focus. We get measured on DU, which is data unavailability. It doesn't happen, all right? That means the file system still has to be able to service data irrespective of what's happening underneath. Yeah. And then, like I said, on the future-proofing side of it. So if you can visit the cosmos.ai, it's our Cosmos community, which is really focused on AI and HPC projects. My kids actually asked me the other day, because I was running this on my phone, and I said, what is that, Dad? It looks like a Discord server, right? And it is a Discord community channel that's run by us, but we have different professors, AI in there. You get to speak to guys at XAI. We've got Elon Musk's companies that are using our tech as well. XAI is one of them, Starlink's one of them, autonomous driving. So again, from a use case point of view, there's lots there, but you get to engage with people that you would normally engage with. All right. From a use case point of view, if you want to talk a little bit more about what we're doing in this space, come and visit Zane and I down at the booth. Okay. Thank you very much.